So today we're talking about hypothesis testing a little bit more. And last time we introduced essentially 7 steps to hypothesis testing. I talked about something that is called a null hypothesis. Then I talked about an alternative hypothesis, a significance level, what the test statistic is. Then we talked about determining for which values we can reject the null hypothesis, how to compute the test statistic, and then how to conclude based on the information that we get from our sample. Okay, so today I just want to give those steps in a more general way. I'm going to try to give those steps in a more general way so that we understand really what the logic behind it is. Okay. I know, so we're at the point of the semester where a lot of people have written a lot of notes and you want to know exactly how much is left to write. There is going to be a lot of exercises that we're doing. So if you copy all of the problems in their full length, there might be quite a bit because the problems are lengthier in their like the énoncés are a little bit longer, but the work is going to be pretty systematic. It's not that long once we get there. Okay, so it depends on how you take notes. All right, so hypothesis testing, we said has 7 steps. So the first thing that we have to do when we are conducting a hypothesis test is to state the null hypothesis. Okay, so the null hypothesis is denoted by H naught, or H0, which is hypothesis 0, which is essentially the thing that we are going to assume to be true, and then we're going to seek evidence to disprove, right? So we're going to assume that something is true, and then what we're looking for is evidence to contradict that statement. Okay? So this is what we will assume to be true, and we'll seek evidence to disprove. Okay. Now, this is usually going to be a statement of the form that the mean is equal to some value, or that the proportion is equal to some value. There's some other types of statements that we can make here, but at least for the introduction of the problems of the topic, you can think of it as it being just an initial assumption based on which you're going to say mu is equal to this. So the mean is equal to that. And then you're going to try to disprove this by showing that the mean is larger or smaller or different. Okay, which brings us to the second part of our hypothesis test, which is what we are trying to prove, but essentially what we're trying to give evidence in favor of. Right? So what that means is we're going to try to get from our sample some evidence for some other hypothesis. Okay. And that other hypothesis is called the alternative hypothesis. So this is the alternative hypothesis. Is denoted HA for hypothesis alternative. And it corresponds to the alternative explanation. The alternative or other explanation for a result. So for example, that could mean you can be showing that the mean is actually larger than the value, or that the mean is smaller than the value, or that the mean is different than the value that you have stated in your hypothesis. Okay, so in the null hypothesis, you assume something to be true. So you assume that the mean is equal to a certain value. And then the alternative hypothesis, the thing that you're going to try to show, is going to be that either your mean is larger than that value, or smaller than that value, or different than that value. Okay, now that alternative hypothesis has to be stated before you even look at the data from the sample. You just want to determine something. So either you want to show that the scores are better than a given score, or you want to show that, I don't know, the performance, like the times in races after a certain training program have decreased. So the average time is lower than a given value or something like that. Okay, so you're really trying to compare to a given value. And so depending on the context, and we're going to talk more about that context and what we mean by it, we're going to determine whether it's either larger than, smaller than, or different than. All right, so that's for the alternative hypothesis. We then talked about a significance level. I'm going to put this here, 3 significance level. Which is denoted by alpha. And it's essentially a measure of the amount of evidence that you want to disprove your null hypothesis, right? So this measures, so this is a measure of the amount of evidence required to disprove the null hypothesis. And so the smaller alpha is, the more evidence I'm requiring. Okay, so if I have a smaller value for alpha, that means that I am going to require my data to be more extreme to provide more evidence if I am going to conclude that the initial hypothesis is untrue, right? So to show that the initial hypothesis is not true, I'm going to have to give more convincing evidence if the value of alpha is smaller. That's because if I think mathematically about what alpha represents, alpha is equal to the probability of rejecting the null hypothesis given that it is true. Okay, so if it happened that the null hypothesis is indeed true, it is still possible that I get some extreme results that make it so that I will still say I have evidence that suggests that it is not true, right? So I know that random chance could give me very extreme results. But if that so the question is whether I am going to reject the null hypothesis based on those extreme results, right? So if I have some extreme results and I have selected that for a certain extreme result, I'm going to reject the null hypothesis, then if my probability is larger, that means that I'm more willing to make a mistake. I'm more willing to say that the null hypothesis is false, even though it might be true, right? So because remember, we are always assuming that the null hypothesis is true, and then we're trying to look evidence to disprove it. But sometimes you can get results that are extreme just by random chance. So there's always a chance that you will reject the null hypothesis, even though it is true, right? Now, what we are trying to adjust with the significance level is how likely we are to make that mistake. Okay, and so when we are trying to quantify how likely we are to make that mistake, well, if we want to be less likely to make that mistake, that means that we're going to require our results to be more extreme so that the mistake happens less frequently, right? Because if I require more evidence, then that means that I'm going to require more extreme values, which are more unlikely to be caused by random chance, and therefore my results should be a little bit more convincing. Does that make sense? So. Okay, so Kay is asking, I don't understand how you can have a probability to reject if it's already given that it is true. Okay, we don't know if it's true. What we're saying is, if it were true, okay, if the null hypothesis were true, like in the example from last week, what was it? In the example from last week, we said if the Canadian men had actually a mean weight of 177 pounds, due to random variation, it would still be possible for a sample of 100 men to have a very high weight, right? Just due to random chance, because there's always variability when I choose a sample of 100 men. Right? So even though H naught is true, even though the null hypothesis is true, it would be possible for me to get an extreme result. Okay. Now, that extreme result is a result that falls in the rejection region that we found. And what we're saying is that we're fixing that value to the significance level. So we're fixing it to be alpha, for example, here 0.05. And we're saying, if my original hypothesis is actually true, then a result as extreme as this one will only happen 5% of the time. Because that result only happens 5% of the time, then it is very unlikely based on that original assumption. And I am going to conclude that that means that my original assumption is not true. Okay, so I would conclude that my original assumption is not true, but it is still possible that even if my original assumption was true, I got one of those extreme results. It's just that it's so very unlikely that I'm going to conclude that that's not what happened. Does that make a little bit more sense, Kaya? Yes, Lori.
Like, how can you realize that the extreme value was just out of chance of extreme values?
You can't. You can't. So essentially what's happening here, what we do with hypothesis testing is just to say, we're assuming that something is true. And based on whether it is, based on that, we're going to try to determine what we should expect. And if our result is in the 5% of the most unlikely results, we're going to conclude that that original assumption was false. That doesn't mean that the original assumption necessarily was false, because you might have been unlucky and you might have just gotten an extreme result due to random chance, right? And so that means that there's always a possibility that you will reject the null hypothesis, that you will say that the null hypothesis is false, even when it is, okay? And you have no way of discerning whether you are rejecting it rightfully or wrongfully, okay? You're just saying, well, my test was built in such a way that I would only reject it when I shouldn't have, alpha percent of the time. But, now that I have rejected it, I can't know whether I made the right decision or not. So in that sense, it's similar to when we constructed a confidence interval where we said our confidence interval was built to include our mean 95% of the time. But once I have computed it, I have no way of knowing whether my interval was right or wrong. Does that make sense? Little by little? A little bit? Okay. Sarah.
Yeah, so it's still for the same thing, but like, okay, using the example of the weight, the average weight or the mean weight increasing, like we found something that was in the most extreme 5%. So we said that our assumption was wrong and that the weight actually increased. But if we found that the weight didn't change, like if we weren't in the top 5%, then does that mean we were right?
Yeah, that
like
means
no matter what happens, we accept the results that we got.
That means that we wouldn't have enough evidence to contradict our original hypothesis. And that's how we're always going to phrase it. We can either reject the null hypothesis, so reject the first assumption that we made, or we can fail to reject the null hypothesis, which essentially just means we don't have enough evidence to contradict it. We don't have anything to suggest that we should contradict that null hypothesis.
Okay, so if we pick our alpha as like the 0.05, like our significance level is 5%. So if we get something in that top 5%, then we just like have, like, no matter what happens, we have an answer pretty much. It's not like something happens and we're like, oh, this doesn't count.
Yes, so we always have an answer, a statistical answer. We always have a statistical answer, but we never know for sure.
Okay.
Right? So it's the same as, so in the example that I gave last week, just to kind of introduce that idea, if you had a coin flip, right, and somebody tossed a coin 20 times and they got heads, 19 of those times, you would say there's something suspicious there. Probably my assumption that the coin is 50-50 is wrong. Now, you can say that it seems like that assumption is wrong, but frankly, you don't have, statistically it looks like it should be wrong, but you can never know for sure because that result, even though it's really, really, really unlikely, could happen, right? So there's always that level of, we think that this is what happened, but really there's always a level of uncertainty. Okay, Laurie.
So by picking a small alpha, it's harder for us to reject the null hypothesis because then it's harder to actually find results that are in this little.
Yes, good. Yeah, that's exactly it. Essentially what we have is that alpha is the probability of rejecting H naught given that H naught is true. Now, given that doesn't mean because H naught is true, it's if H naught were true. Okay, so it's not because H naught is true, this is the probability of rejecting H naught, is if H naught were true, what would be the probability of rejecting H naught? Okay, and what we don't know is whether this is true or not. Okay, so it's a little bit of, mental juggling about how we need to interpret this, but I think little by little, it should become a little bit more comfortable to think about. At the same time, I don't want you to get too comfortable in thinking about it because it is important that you realize that there's always some level of uncertainty and always something that you don't know 100% for. Okay, so it's always something that you need to think about, and answer to a statistical question with statistical evidence never gives you a full answer. It just gives you, it suggests an answer, but because all processes in life have a certain level of randomness, well, your conclusions always have a certain level of uncertainty. Okay. All right, so then we have 4, which was a tested, so like stating the test statistic. That was a 4th step. The test statistic. And its distribution. Okay, so stating the test statistic and its distribution, that means the value that we will compute from our sample and how we should expect it to be distributed, right? So for example, that could be x minus mu divided by sigma over square root of n. It's essentially just stating what we should expect from the values that we compute from our samples. Okay, so here what we're doing is stating how we expect our sample statistics, whether that is a mean or a proportion P, to behave. Okay, so to behave or to be distributed.
Okay, quick question. Why is it p hat and not just normal p?
Because it's the sample one.
Okay. Oh, right. Sorry. I'm like writing and not even.
That's good. That's good. Means you're thinking while you're writing, which is nice. Okay, so the reason that we try to state why, like the way that our sample statistics are behaving or distributing, is that this allows us to predict what would be normal from what would be unusual. Okay, so what would be usual for us to see within a sample, what would be unusual for us to see within a sample. This is the part that allows us to determine how to gauge that.
Miss?
Yep.
What's the last word you wrote? Sorry.
To be distributed.
Okay, thank you.
All right, then we're gonna build the rejection region. Oh yeah, Laurie.
It's just a really quick question. Is it always going to be the X bar for when it's our sample? Because at one point, I think in the homework, I just put X. So are we losing points?
It's always X bar when it's the sample average. I think in the homework, right now that you asked me about question number 1, there was just a capital X, and it's because it was missing the X bar. But if you make the mistake at some point, I won't be too mad about it. It's just that for notation, it's useful to distinguish X, which is just one instance, from X bar, which is an average of several instances. So find the rejection region. When we find the rejection region, what we're looking for is the most extreme values that our sample statistic should have, right? So this is where we determine which ones are my unusual values. Yeah, that's it. So these are the values. The rejection region corresponds to the values of the test statistic for which we will conclude that H0 is not true. So for which we will reject H0. This means that these are the values, the alpha percent, alpha most extreme or unusual values. Okay, because we will reject it if our results are suspicious, so if they're very unusual. The 6th step is fairly simple because you'll always have a formula for it. It just means you're going to have to compute the test statistic. Okay, so that's pretty straightforward. You have to compute the test statistic. So that's it. You just compute it for your sample. And then in step number 7, well, you have 2 very clear things that will allow you to draw a conclusion. You have a rejection region and you have a test statistic. And so if your test statistic falls in the rejection region, you reject the null hypothesis. If your test statistic falls outside of the rejection region, then you do not reject the null hypothesis. Okay, so here you conclude. I'll specify how. So if the test statistic falls in the rejection region, then you reject the null hypothesis. But if the test statistic is not in the rejection region, then we say that we fail to reject H0. Okay. I want to be very clear that we never accept any hypothesis. Okay, so we will never conclude that one of the hypotheses is true. Okay, neither the null hypothesis nor the alternative hypothesis, because our evidence only suggests whether we have enough things to contradict the null hypothesis, and that's that. Okay, so if we reject the null hypothesis, all that means is that we have enough evidence to suggest that that hypothesis does not hold, but that's it. Okay, and then if we fail to reject the null hypothesis, what we're saying is I don't have enough evidence to contradict it. I still don't know if it's true or not. Okay, it's just my data doesn't seem to suggest that I should conclude that it is false. Okay, so it's always like a little game of like logic and measuring of uncertainty, but we're going to see that the problems are really like algorithmic. You just follow always the same procedure. It's really not too complicated a procedure once you have started like getting the hang of it. But whenever you have to kind of like think about the logic of this again, just go back to this list of steps and try to understand where all of them come from, because if I ever ask you to interpret something, that's where things, that's where you need to make sure that you understand what you're saying, right? Okay, do I have any questions? I don't see any questions, which means I'll introduce the first set of instructions for a test hypothesis, and then we'll do an example, and then I'll do a couple more. You'll see there's a couple of different types of hypothesis tests. What's important is that you pay attention to when we use each one of them, okay? So it's the same kind of idea as when we compute confidence intervals. We have to pay attention to the assumptions that we make. All right, so here is the first one. We have test 1. And this is a hypothesis test for a normal distribution with known standard deviation. Okay, so I'm going to assume, so the assumption is that the population is normally distributed and the standard deviation, the population standard deviation is known. Actually, population standard deviation sigma is known. Okay. So the null hypothesis in this case is always going to be for the mean that you are trying to look for. So you're going to check that mu is equal to some value. Okay, so I'm going to call it mu0, but this is just essentially the value that you're comparing to. Okay, so for example, before our null hypothesis was mu is equal to 177, right? So that's the value that you're comparing to. And then you can have several types of alternative hypotheses, which I'm going to list in just a second. Oops. But before I list the alternative hypothesis, I will state the test statistic. It will be clear why I'm doing it in this order. Just bear with me for a second. So the test statistic in this case is going to be Z, which is equal to, from your sample, X bar minus. Now you're assuming, or will be assuming, that the null hypothesis is true, which means that we're going to be assuming that the mean for a population is equal to mu naught, right? So that means that here you're going to subtract mu naught, and you're going to divide by sigma over square root of n. All right, and this, because you know that the original population is normal, and because you know the standard deviation of the original population, so you don't have that variability of the sample standard deviation coming up, then you know that this is going to follow a normal distribution with parameters 0 and 1. Right? So this is just a standard normal distribution. Now, the alternative hypothesis, sorry, is the thing that we're trying to propose as an alternative. So that might mean that the mean that we're interested in is actually larger than the value that we're comparing it to. This is what happened in the example that we did last time, right? So we said mu is larger than 177. So mu is larger than mu naught. But it's also possible that we would try to show that a given mean is below a given value and not above that value, right? So that means in that case, we would have mu is smaller than mu naught. And sometimes it is possible that you're trying to show that the mean is not necessarily higher than the value or smaller than the value, but rather just different than a given value, right? So sometimes you're going to say that this is mu is different than that value if you have no reason to believe or to try to show that the mean is either larger or smaller than. These two are called one-tailed tests, whereas this one is called a two-tailed test. Now, the reason that I want to distinguish between these three different alternative hypotheses is that for each of them, the rejection region is going to be slightly different, okay? So this rejection region is going to be, if I'm trying to show that mu is larger than mu naught, then that means I'm trying to show that actually my sample suggests that the mean should be larger than the value that I'm comparing it to, right? So that means that I should only reject if I get extreme results, but extreme results that are high, right? So I will reject that mu is equal to mu naught if I get extremely high results that suggest that my mean is actually larger than the value that I'm comparing it to. Which means, because we know that this is a normal distribution with parameters 0 and 1, that we will reject if the value of z, the test statistic, is larger than z alpha. Remember, we said that if this is the probability, like if this part over here is alpha, which is the probability of rejecting if H naught is actually true, this will be z alpha here. Then, if I'm trying to show that my mean is actually smaller than the comparison value, smaller than the value that I'm comparing it to, then what I should look for is evidence that suggests that my mean is smaller than that value, right? So that means that instead of looking for values that are extremely high, I'm going to look for values that are extremely low. And those are the ones that are going to suggest that my mean is actually below the value that I expect it to be, which means I should look for values that are somewhere around here. Okay, so in this case, I will reject if z is smaller than minus z alpha, because I know this to be symmetric, right? So this is going to be minus z alpha. Okay, so we're almost there. And then if I want to show that the mean is different than mu naught, but I don't necessarily want to show that it is specifically larger or specifically smaller, then I'm going to have to reject my null hypothesis. I will have enough evidence to say that my null hypothesis is not true if I have extreme results that are either too high or too low, right? So both of them are going to be considered as evidence. I'm going to have results that are too high or too low. But I still want the probability of being in the rejection region if H naught is true to be equal to alpha, which means that I'll have to split that alpha in two, right? So I'll have alpha over 2 at the top, alpha over 2 at the bottom. So each one of these is going to be alpha over 2 is alpha over 2. So that means that I will reject my null hypothesis if Z is larger than Z alpha over 2, or Z is smaller than negative Z alpha over 2, which is the same as to say that I will reject the null hypothesis if Z in absolute value is larger than Z alpha over 2. All right, so how are we doing with this? Yes, Sarah.
I'm getting a little bit confused with the last one. Like, how is it one or the other? Like, shouldn't it be both? That it's like neither in the top or the bottom?
Well, only one of them is going to be true, right? The value of Z cannot both be larger than Z alpha over 2 and smaller than negative Z alpha over 2.
Okay, wait, isn't
Just like a value can't be larger than 1 and at the same time smaller than negative 1.
wait, okay, the second one, Z being smaller than negative alpha over 2
Mm-hmm.
isn't, wait. So wait, we want it to be in the shaded in region?
Okay, so if it is on the shaded in region, that's when we reject our null hypothesis. That's when we say that we have enough evidence to suggest that the null hypothesis is not true. Yeah.
Okay, sorry,
So-
I was thinking about being in the middle.
Okay, no. So it's going to be like if I have an extreme result, then I reject the null hypothesis.
Okay, yeah,
Yeah.
sorry.
So you can think about it like, okay, so if you like formulas, this is the way to remember it. Okay. If you like drawings, this is the way to remember it. Now, I personally like the drawings because it's really easy to just like scratch it and just kind of like figure it out. Whereas the formulas, you have to remember what orientation it's going in, and at the same time, you have to remember whether it's alpha or alpha over 2, and you have to just make sure that everything that you remember is exactly the right way. Whereas when you draw the figure here, even if you don't remember exactly what's going on, you can kind of figure it out based on just logic. Okay, so if you can, I just think it's a better investment of your mental energy and time to think about the logic of it and then try to remember how to draw the figurines. And then once you do that, it's going to work exactly the same for all the tests. Okay, so all that you have to remember eventually is this. And most often than not, I'll give you that. So as long as you know how to draw, you're good to go. Yes, Laurie.
So are we the one who decides which test, if it's like a one tail or two tail?
Yes, based on context.
And like based on the context. So like,
Yes.
depending on the problem, one problem will be better, or statement that the questions that you ask us will be better to use whichever test.
Yeah. So based on the question that I'm asking, it's going to be, it's not always obvious. I'm not going to lie. It's not always obvious which ones you're going to use, but that's what you're going to practice, right? So you're going to determine, and this is a classic final exam mistake, like you do a 2-tail test instead of a 1-tail test, and like, it's fine. It's not the worst of the mistakes, but it is something that you need to practice to identify, what you're actually trying to determine. All right, so I have a problem here. You can copy it all now, or you can just try to think about it. And the recording is going to be available anyway. So if you want to go back and copy the problem later, that's fine. For now, I would suggest that you try to solve the problem, or that you just copy the essential information. So I'll give you maybe 2 or 3 minutes. Yeah, 2 or 3 minutes to start thinking about this problem, to try to set up the steps. Okay, so just try to follow the steps and see how you can start trying to perform the test yourself. All right, it's fine if you don't know exactly how to do it now. It's the first one that you have to do on your own, but try to get started. Okay, so I'll start talking about how to address this type of problem. The first thing that I want to say is before you ever try to figure out what type of test you're performing, if a 1-tailed or a 2-tailed, try to ignore the data that is given with respect to the sample. Okay, the type of test that you're conducting does not rely on the data that your sample gives you, so on the results that you have from your sample, but only on the question that you're trying to answer, right? So because your one tail versus two tail test only relies on the type of question that you're trying to answer, you should try to ignore the data, because the data is going to suggest to you what type of test you're going to conduct, right? So imagine that I were to ignore the data. Okay, I'm just censoring what we know for the sample. Okay, so the question is, we have a manufacturer of sprinkler systems used for fire protection in office buildings claims that the true average system activation temperature is 130 degrees. Does the data contradict the manufacturer's claim at a significance level alpha is equal to 0.01? Okay, you can see that here the question is already formulated. You already have the alpha. You can already do, I think, up to step number 5 in the hypothesis test, and only at step number 6 should we start caring about the data. Okay, now why do I say that? Because often when you ignore that like the information that's given for the data, that gives you a way of thinking about the question instead of thinking about the data right away. Because we're really prone to just like go straight to the data and be like, the data suggests this, and then like we want to confirm what the data is telling us. Here we want to first look at what the question is, build everything based on that question, and then we're going to answer the question using the data. All right. Can I see a yes, please, for everybody that understands this? Haven't done this yet today. Took a while. Very well. Okay, so the first thing that we're going to try to formulate is our null hypothesis. So the null hypothesis is what I'm going to assume to be true. Okay. Now, in the null hypothesis, I'm going to say that mu, which is equal to, and I'm going to ask you in every null hypothesis that you state to state in full words what mu represents. Okay, so you just write mu is equal to, you explain what it is, and then you make the statement for the null hypothesis. So here, mu is the true average system activation temperature. For the sprinklers. Okay, and so what we're trying to test, like the hypothesis that we're going to start with, is that mu is equal to 130. Okay, because what we're trying to determine is if we contradict the manufacturer's claim. The manufacturer's claim is that the system activation temperature is 130. So this is what we're going to assume to be true. All right. Can I see a yes for everybody that understands this, please?
Wait, I have a question.
Yep.
Are we calling this mu or mu naught? Or like in the steps, do we just call it mu naught because we didn't actually have a number?
Okay, yes, so mu is the parameter of interest for me. Mu naught is the comparison value. Okay, so this here is mu naught because mu is unknown. Okay, mu is the parameter for our population, which we don't know. And what we're checking is if it's equal to this value mu naught. Okay, Lori.
Yes, and it's really an odd question, but why is it in Fahrenheit? Because like it should be in degrees Celsius if it's like temperature when like it starts, because I don't think 131 Fahrenheit is a lot, because when we just start the oven, it usually starts at like 190 or something.
Yes, but it is not normal for the I mean the sprinklers would not be in the oven. They would be in the room, right? So if the temperature of a room gets up to 130 degrees Fahrenheit, then you should assume that there's something else going on. Okay, so yes, definitely. I mean, if the temperature of your room is 130 degrees Celsius, it's a little bit too late for the sprinklers to do their thing. All right. So then the alternative hypothesis. Here's where things start to get tricky. That was quick. We need to determine whether we're doing a one-tailed or a two-tailed test. I would like for everyone that thinks it's a one-tailed test to vote yes. So yes for one-tailed, no for two-tailed. There's contention. So it's a two-tailed test because we're not trying to show that it is larger than a given value or smaller than a given value. Although we're trying to do is determine whether the claim that the manufacturer made is false. Okay, so that means for us that we're trying to determine whether the claim is false. We're trying to determine whether the temperature is not 130, which means it's different than 130. Okay, now this is why I suggest that you try to ignore the data beforehand. Okay, because when you see the data, you already see right away, really clearly, whether the value is larger than or smaller than, and it's always only going to be either larger than or smaller than. Okay, so it's always going to suggest a direction for the alternative hypothesis. Do not try to take that into consideration. Okay, try to ignore that data, try to formulate your alternative hypothesis before looking at the data, and then you can look at the data. Okay, so the alternative hypothesis here is that the true average system activation temperature, we don't have to specify that again here, is equal, well, not equal, sorry, to 130. So it's different than 130. So no need to state the full parameter again. And so this means that it's a two-tailed test. The third thing that we have is that the alpha here is equal to 0.01. Then we have to state the test statistic, which of course here is clear because we have only seen one test, so that's nice. That's going to be Z is equal to X bar minus mu naught, which is 130, okay, divided by sigma over square root of n. And this follows a normal distribution. The idea behind stating the distribution here is that that already makes you think about what type of values you're going to look for in the rejection region, right? So we're going to see that here because it's a normal distribution, then we're going to look for Z values in the rejection region. If we had a T distribution, for example, then we would have to look for T values in the rejection region, all right? Sarah.
Are we supposed to fill in the sigma right away, or is the standard deviation we got from the sample?
The standard deviation is from the population. Okay, so actually I'll include this justification here because it's useful to know what the distribution is. But here you have that if the distribution of activation times is normal with standard deviation 1.5 degrees Fahrenheit, that means that this is the population distribution and the standard deviation is for the population.
So like, why don't we write it in right? Like, are we supposed to write it in? Does it matter?
You can write it. It doesn't make that big of a difference. But because a lot of times we're going to have that this value is given by the sample, maybe it's good practice to try and avoid entering values before it comes to step number 6, which is when you actually enter all the values for the sample.
Okay.
And so here, so the justification for this distribution is that the population is normal. And the standard deviation is known. Right? So I am checking essentially that the assumptions for this test are satisfied. Okay, so because the population is normal, blah, blah, blah. Then I have 5, which is find the rejection region. If I'm going to find the rejection region, and check this out, I don't want to necessarily learn it by heart. I'm going to try to find this myself. I have that the rejection region, in this case, I have a two-tailed test, which means I'm going to chop things from top and bottom here. My alpha is 0.01, which means that I'm going to chop 0.005 from each higher and the top and the bottom value of the top and bottom chunks of my distribution. And so that means that here I'm going to look at the value that separates the 0.005 top percent from the bottom 0.995. Okay, so I'm going to look for this area here to be 0.995. You see. Okay. So if this is what I'm looking for, then I'm going to scan my table. Remember, and we're looking for the filling to be equal to 0.995, which means 0.99. This is 0.99559, so it's before this is going to be around here. Right? So it's exactly between 0.9949 and 0.9951, which means I'm going to look at the value that's exactly here. And that means here 0.99, this is 2.5, and the value between 2.57 and 2.58, which means this is going to be 2.578, 75, sorry. This means that this is going to be so the region in the middle is going to be 99%. If this is 2.575 or minus 2.575, this is going to be my rejection region. Okay, which I can phrase as Z being larger in absolute value than 2.575. Okay, again, if you already know that, like, how to find this value based on the formula, that's fine. But I find the drawings useful anyway to find the probabilities, and so I might as well just do the drawing to make sure that everything's right. All right, so this is my rejection region, which means that I will reject H naught if this is true. In step number 6, I have to find the value for my table, for my sample. And so here is the point at which I start using the data for my sample. Okay, that's the only point at which I need to use it. And so in our sample, we have that Z is equal to X bar, which was 131.08 minus 130. I also said 0.8 and I wrote 0.5, so of course it's not great. Divided by 1.5 over square root of 9, which is equal to 1.08 divided by 1.5 divided by square root of 9 is 1.5 divided by 3, which is 0.5. And dividing by a half is the same as multiplying by 2, which means that this is 2.16. And then I can conclude.
I have a question.
Yeah.
If the standard deviation that we had was not for the population, but for the sample, because it's normally distributed, can we still apply this standard deviation in our?
No, because there's a level of variation that comes from the fact that the standard deviation is also from the sample, so that there's also variation from the sample itself, which means that if we have a population that is normally distributed, but for which we only know the standard deviation of the sample, we'll have to use the t-distribution. That's one of the next tests that we're going to do. Okay, so it's similar to, it's always going to be very similar to the confidence intervals. Okay, and so here we're going to conclude that we fail to reject the null hypothesis, right? So we have that 2.16 is not larger than 2.575, which means that we fail to reject H naught. I'm going to ask you to always try to interpret in a little sentence what this means. And for us, what this means is that there is not enough evidence to suggest or to contradict the manufacturer's claim. With a significance level of 0.01. Now, let me be very clear that the 0.01 is not the probability that we're right. Not at all, okay? It's not the probability that we're right. It's simply the probability to make a mistake if the original assumption was true, okay? That doesn't have anything to do with whether we're right or not. We have no way of knowing whether we're right or not. All that we can say is that if it was actually true, then I wouldn't reject the null hypothesis with probability 99%. Okay. All right. So I'm going to write a second test for a second set of assumptions. I'm going to copy paste it from the previous one because it's actually pretty similar, except for one extra assumption. Let's copy. And then you'll have another problem to do. Yeah, okay. So here, in test number 2, our assumption is going to be that the population is normally distributed. We can drop that. And we can drop that the standard deviation for the population is known. All that we have to say is that the sample is large. Remember, because this is from the central limit theorem, and we're going to say that this is true for a sample that's larger, that has 30 observations or more. So give me 1 second. Okay. At this point, the only thing that's going to change, pay attention here, is that in my computation of the statistic, I'm going to have S instead of sigma. Okay, but that relies on me having a large sample. Okay, so really important to note the differences here. Here, this is the standard deviation like that. And the condition here is that the sample has to be large. The rest, though, is the same because my distribution is the same. And so what I should expect from my sample should be the same. And so the alternative hypotheses are going to be the same. The rejection regions are going to be the same. But what's important is that I can only apply this if my sample is large. Okay. And please, as soon as you're done writing, vote yes. Exactly, Kea. So if the sample is large, we are allowed to use the sample standard deviation in order to estimate the population standard deviation. There you go. So this is the next problem, which I would like you to start working on. Again, you don't necessarily have to copy the whole thing. Now for this one, you're going to have to do two tests, one with a level of significance of 0.05, one with a significance level of 0.01. And what we'll do is I'll give you the rest of the class to think about this problem. You can send me your answers through private chat here. I'll tell you if it's right or if it's wrong. If it's wrong, I'll try to point you in the right direction. If it's right, then I'll just tell you that it's right. And then I'll give a very short correction of this next class, right? That's what we'll do for the rest of class today. So yeah, you in the participation tab that I'm going to open, in small assessments on Teams, you'll have to give the answer to two questions. The first is, what's the conclusion for a significance level of 0.05? And the second one is, what is the conclusion for a significance level of 0.01? Okay, so you have to think about that. And then I want you to think about why you got the results that you got. Okay, so you're going to get one result for a significance level of 0.05 and then a result for a significance level of 0.01. And I want you to think, to kind of just reflect on what these results mean and why they are either the same or why they are different. All right. And I think that's that. I'll see you on Wednesday. I will have office hours today. So if you have any questions, we can see that then. And don't forget to post your surveys because they have now been corrected and you can now start distributing them to your class. Also, make sure that you try to complete all the surveys for all your teammates, just as you want a lot of data for your own survey. Your classmates also want a lot of data for their surveys. So each one of your answers counts in terms of what can be analyzed for every person. All right.